Hello from the ForceTronics YouTube channel and welcome to building a wireless bipolar stepper motor driver circuit, and this will be part 2 in a 3-part series. Before I get started, if you want to access exclusive ForceTronics content, whether that's longer videos, code from videos, hardware design files, bombs, schematics, check me out on Patreon where you'll find exclusive content from various video series as well as this one. If you haven't already, please subscribe to the ForceTronics YouTube channel. And if you like what you see here, please hit the thumbs up. All right, let's get started with part 2. We have a lot to cover. Okay, as I mentioned in part 1, what we're designing here is a bipolar stepper motor drive circuit using the TB67 bipolar stepper motor driver IC, which has a lot of nice features, including microstepping, which I talked about in part 1. And then the microcontroller we'll use to pair with this motor driver IC is the ESP32 S3 version. And so we'll use this for our wireless connections as well as the command and control of the motor drive IC. And as I mentioned in part 1, we tuned our motor drive IC design for a specific bipolar stepper motor, and I list the model number right here, the 17HS15-1504S. And of course, you can use this for other stepper motors, but you might have to tweak a couple components for the driver IC setup to tune it for what you're trying to do. Okay, from all the material from this 3-part series can be found on my Patreon page, whether that's the Arduino IoT cloud code, the schematics, the PCB files, the Gerber files, the BOM, etc. That'll be available on Patreon. The hardware files will be available on Patreon as I speak, as you're watching this part 2. And then when part 3 comes out, the Arduino IoT code will be available. And in part 2, we're going to do a demo and take a look at our board. And then we're also going to go into detail of the hardware implementation of the board. The whole board, but we're going to spend a lot more time on the TB67. And then in part 3, we'll look at the Arduino cloud code and go over that. And then we'll discuss thermal management for the hardware. Okay, what you're looking at is a demo video for the board and the cloud control software. So right now we're looking at the board. So let me just do a quick introduction for the board, but we'll go into more detail on the hardware next after the demo. But the power input is on these 2 screw terminals up here. The board is configured to handle 12 volts to 18 volts. We have a big capacitor for handling the current transients that the chip uses to power the motor. So that's why we have that big capacitor there. Right here is the actual TB67 IC, and here this connector is the motor connection, the bipolar motor stepper motor connection, and there's 4 wires, right? Because there's 2 coils, that's why it's bipolar, and we have a wire for each end of the coil. You can see we have nice fat traces for the high current flow that's going through these wires. What else should I mention? Here's the 3.3 volt regulator, here's the power LED, and then we have the ESP32 module, of course. We have some LEDs that show when the motor's running, if it's turning clockwise and counterclockwise, and then various supporting components that we'll cover later in this video. Okay, so first let's look at the power supply. I have it set up at 12 volts. And here we're looking at the power supply. It's in standby mode, meaning the motor's not running. In standby mode, it draws about 100 milliamps to 150 milliamps. A good portion of this, though, is the ESP32 module because I have the cloud code loaded on it. So it has to maintain a constant Wi-Fi connection. And so a lot of the ESP32 current is what we're seeing in the standby current. When the motor's running, that draws about 500 milliamps to 700 milliamps, and it does vary a bit because the current isn't constant when you step. All right, there we can see the current went higher for a bit and then went back lower. All right, let's look at the motor. So here is the stepper motor that I'm using, and I shared the model number for it on the first slide. But basically, I clipped on a PCB for an LED design that I did a while back. But the idea is just so we can see that board spin, so we can see that the motor's doing something. Next, let's look at our cloud control dashboard on a computer. So here it is. Even though I'm right next to the board, I'm controlling it through the cloud. I'm connected to my Wi-Fi, and the board is also connected to my Wi-Fi. And so I set up this dashboard in Arduino IoT Cloud. And if you're not familiar with Arduino IoT Cloud, I encourage you to check it out. I have other video tutorials that use it and go into it in more detail. But I set up this simple dashboard, and I'll run through this in more detail in part 3. But you can set the step count. So I set it for 7,000 steps. You can then select the direction, clockwise or counterclockwise. This button then executes the steps. And then this state just flashes green when the motor's running and red when it's off. And then I had the ability to read some diagnostic pins. The ESP32 can read some diagnostic pins from the TB67, so I can alert the user if there's some type of issue with the motor. So let's first turn the motor clockwise by pressing the button. We see the motor state turn green, and we can see that the motor is spinning clockwise. And we can see the LED on the board lit up. Now it's stopped. Now I'm going to press counterclockwise and execute. So now we're seeing the motor spin counterclockwise. So pretty cool. So you can imagine doing this from like you can imagine using this for like home automation type applications where if you want to be able to open and close a doggy door at your house when you're not home, or raise and open blinds or something like that. That's where this motor drive can come in handy. And it's so easy to connect to Wi-Fi or Bluetooth using the ESP32. All right, now I'm going to simulate an error condition. So I pulled the connector off. So now the motor's not connected. So notice when I press go, this motor open indicator turns red. So it's basically the ESP32 detected that the motor's drive IC is saying, hey, I'm not detecting coils for current to flow through. So it throws that error that the motor's open. All right, that's our short demo. Let's dive into the hardware design for the board we just saw. Okay, what we're looking at is the schematics of the design. So this is done in EagleCAD software where I do my PCB layout. So that's why that's the interface we're looking at the schematic in. And these green wires represent electrical connections between different parts, capacitors, resistors, and this represents the ESP32 IC. Where you see a green connection with a label on it, that means wherever else you have that label, that represents an electrical connection. So the ESP32, I've gone over in more detail how to implement that into designs, as well as how to program it in other videos. So I'm not going to go into super detail here. You can see some notes here. But basically, this J2 is a 6-pin 2x3 header, and this is where you would do the programming. So I don't have a programming chip on this design, so you'd need a programming board like the ESP Prog board to program this. But it connects to the enable or reset pin. It uses UART to do the programming, and then it needs to control IO0, which is known as a strapping pin, to pull it high or low at the right times to enter programming mode. These capacitors are recommended by the data sheet. And then here's my various connections. So MD stands for motor drive. So LO2 and LO1 are the pins that indicate diagnostic states. So there's 4 different states. There's good, and then there's the 3 others represent errors. We saw an example of the open error that was detected. We have the reset pin, so we can reset the motor drive. I don't actually use this in the example. We have the enable pin. The enable pin is important because if you leave the motor drive enabled all the time, you're going to have constant high current flowing through the motor, and it'll actually cause the board to heat up pretty much. So I enable the motor when I'm about to use the motor, and then once I'm done using it, I disable it. This is the strapping pin for programming it. I just mark it so I know not to use it. This is actually the signal that steps the motor. So a logic low to high transition triggers a step. This pin triggers the direction. So 0 is one direction clockwise, 1 is another one counterclockwise. So the order would be as if I wanted to move the motor, I would first enable it, I'd set the direction, and then I'd set my steps, which will be like a pulse train. This DM0, DM1, and DM2 pins, this sets the step behavior for the motor. So in part 1, we talked about full step, half step, and micro step. That's what these pins configure the motor driver to do. And I'll use them configured for the max microstepping resolution of 1/32. So you have high resolution control over the motor's movement. If you want to configure it differently, go to the data sheet. That's where it tells you how to configure these pins. This pin is for controlling the motor clockwise LED and then the counterclockwise LED. So when the motor's in motion, I turn one of those LEDs on. So that's our ESP32 schematic. Here is our J1 connector. That's the screw terminal where our bus voltage connects. So we have 12 to 18 volts that we can use to power the design. The TB67 chip can actually handle higher voltage power supplies, but because of other parts on the board, including the 3.3 volt regulator, I'm limiting it to 12 to 18 volts. This is our circuit for a power LED. Whenever VCC and ground is applied, this LED will be on. These are the LEDs that are controlled by the pins we just looked at from the ESP32. So I'm just using a MOSFET as a switch. When I turn this pin, the CW LED pin on the ESP32 to high, that makes this MOSFET act like a short, so this LED will turn on. These 4 pins are the motor connection pins. So we have the A coil and the B coil, so 2 connections for each coil. Here's some pins I just added that might be useful. You can access the 3.3 volts, you can access ground, and you can access the UART pins if you want to use them for debugging. And then finally, we have the 3.3 volt regulator, which takes the bus voltage and turns it into 3.3 volts for powering the ESP32. And these capacitors bypass capacitor values I got from the data sheet for the 3.3 volt regulator. And then we have a Zener diode just to protect that 3.3 volt bus from overvoltage conditions. Okay, here's where we're going to spend the most time, and that's looking at the implementation of the TB67 motor drive IC. Now I'm going to step through this chip pin by pin, and you're going to see some notes that I'm going to talk to. Now, where did I get these notes from? I didn't just make them up myself. I got them from the data sheet. So I read the data sheet, and I always stress that in my videos. And this is some of the decisions I made for configuring this chip to drive the motor that I showed in the demo. This first pin, EP, is really the pad, the ground pad on the bottom of the chip that's used for thermal management. So here's actually a zoomed in picture of the bottom of the chip. So that EP pin is really for this pad. And you need to have this pad have a good connection to your ground plane on your PCB so it can dissipate heat. Depending on how often you drive the motor will depend on how hot that gets. And we'll talk about thermal management more in part 3. Next, we have the LO2 and LO1 pins. This is what gives us our diagnostic states. So the ESP32 reads these pins, right? So the TB67 drives these to a certain state and the ESP32 reads those. And we demonstrated the motor open condition. And you can see the states of the pins when we look at the code. We don't use the MO pin. MO pin provides info on the motor's electrical angle. So I didn't need to use that for their data sheet. If that's something you're interested in, you'll have to look how to implement that in the data sheet. Next, we have the reset pin. I pull it low. If you send an active high to it, it'll reset the chip. I don't use it in this demo. Then you have the enable chip, the enable pin, I should say, and I already talked about that, but I pull it low so the motor is not enabled to start out with, and then you have to actively pull it high to enable it. And that just applies power to it, so then you can step and choose the direction. Once again, to avoid high current flow or high power usage, I recommend disabling the motor when you're not using it. This pin they call clock is the step signal, so it's like a clock signal, but low to high transitions trigger a motor step. Next, we set the direction. 0 is clockwise, 1 is counterclockwise. Next, we have the D mode pins, right? So these are controlling the step type. So you can do full step, half step, and then various micro step settings. I set them all to high for the highest resolution step setting of 1/32. If you want to set it for something different, you can. It's tied to the ESP32, so you can change that however you want. Next, we have a couple unused pins, not connected, not connected, not connected. OCCM is if you want to use a clock, so this chip has a clock and it uses for timing. If you don't want to use the built-in clock, you can input your own clock. I tie it to ground to signal to use the input clock at its default settings. This VCC 1 and 2 is actually an output voltage from the chip, and I label it as V+. So the chip has its own internal voltage regulator, so it outputs a 5-volt voltage bus, real low current, so you can use that as a pull-up for its various pins, as well as to set its output current. So just keep in mind that this is not an input pin, it's an output pin. Next, we have the VREF, A and B. So they have a reference voltage that tells the chip what the max current of the motor is. So the chip does not source more current than the motor needs, which could possibly damage the motor. And so what they do is they allow you to set the max current for each coil, A and B. I'm going to use the same value. That's why I have the pins pulled together. But here's the formula they give you for setting your max current. So Imax equals 1.25 times Vref. And so they're saying to set Vref, use a voltage divider, and you can use their output 5-volt bus to do that. So what I do is I times 5 volts by my voltage divider value, which I use a 3.24 kilo ohm resistor and a 10 k ohm resistor. And if you do the math here, you get about 1.5 amps, which is the max current of this bipolar stepper motor that I'm using. So if you're using a different stepper motor that has a different max current, you'll want to change this voltage divider around, and you can use the same equation. I also have pins so you can measure Vref, because Vref represents what the max current setting is. So if you want to make sure you have it right, you can check it here with a DMM. All right, next we have some ground connections, another no connection, and then we have the power supply for the B coil, and we have another one for the A coil. So this VCC is the voltage bus for the design, the 12 to 18 volts. And this chip, once again, uses separate input supplies for the B and A coil. For me, my A and B coil are the same, so I use the same supply and the same max current setting. Over here, we have our bypass capacitors. So we have the big 68 micro ohm electrolytic capacitor that I showed in the image. And then I also have in parallel with it a 100 nanofarad capacitor that eases any current ripple that might be on the large capacitor. Then I have a Zener diode that's rated for 19 volts. So this helps make sure we don't apply more than 18 volts to our design, which could damage the linear regulator, which is only rated for 20 volts. But also, the data sheet for the TB67 says you could have some back EMF, and that's caused by current storing energy in the motor's coils. And when you stop stepping, that energy has to dissipate somewhere. And so they warn you about back EMF. So that's another reason I have this Zener diode on, is so I know that any back EMF won't cause this voltage level to go too high. These pins down here are for the actual current flow through the B+, B- coil, and A+ and A- coil. And they double up the pins so they can handle higher current. So that's why you see these pins shorted together. So we have some grounds. We have A+, A-, B-, B+. Over here we have the power supply for the A coil. We already talked about it for the B coil. We're just going to use the same bus for both. Now here we get into various setting pins. So you can see a non-connected pin, you can see a ground pin. But if you look at this LTH pin, this is a pull down with 100K for standard automatic gain control threshold. So AGC stands for automatic gain control. And it's one of the nice features of this chip, which gives you really tight control over the current flow. So this is just setting the standard threshold for automatic gain control. And I'm using automatic gain control in this setup. This boost pin, boost sets ramp rate to max current for torque increase. So what this means is for the maximum current, we're not going to get to the maximum current until we do at least 5 steps. So it sort of controls the ramp rate of the current. And that's just so we don't slam to the max current right away. And you can change this to other settings, but I'm using it tied to 5-volt bus. And that sets this 5 steps to get to the max current. And so a lot of these settings have to do with the automatic gain control functionality. So for instance, this CLM pins, they set the bottom current limit for automatic gain control. And so what I did is I kind of gave you the option that you can adjust it if you don't want to change this design to whatever you want it to be. So the CLM 0 pin is tied to high, so you can't change that. It's tied to VCC. But I list these other ones, the CL1 pin, I have it with a pull up and a pull down resistor. So what you could do is you don't want both of these resistors here. So you could put one or the other, and you can see it sets the bottom limit for the automatic gain control current. And then you could also short it to V+ without a resistor here, just put a big bead of solder across it, or to ground to change it to different settings. So 80%, 75%, 70%, and 65%. And so what this means is what automatic gain control does is it says, okay, I'm not going to try to put the max current flow through it if you're not using it at a high torque setting, meaning if there's not a lot of torque on the motor, not a heavy load, let's not have max current flowing through it. And they do this to conserve power. So if you use automatic gain control, that's what it's doing, is it's based on the torque needs of the motor, it ramps the current up and down. And so what this setting is doing is saying to automatic gain control, don't go below these settings. And the reason you might not want to do that is you then might not ramp up quick enough to get to that max current when you need the torque quickly. And then we have the AGC control, which we have it set up so that automatic gain control is on. There's some different options for automatic gain control, and you can find those in the data sheet, but I'm just turning the automatic gain control on. The last thing I'll mention on this design is this motor drive uses 5-volt logic, and that's why it has a 5-volt bus, but our ESP32 uses 3.3-volt logic. That's why I have these pins over here pulled up using 3.3 volts, because I don't want 5 volts applied to the ESP32. I don't have any level shifters though, because we do have the ESP32 sending signals, the step signal namely, to this chip. And the reason I don't have level shifters is the chip's data sheet clearly states that 2 volts and higher, 2 volts to 5.5 volts, represents a high logic level. So I didn't see the need to have a level shifter because 3.3 volt logic will be read as a high. All right, let's look at the PCB layout. So here you're looking at the board, the PCB layout in my EagleCAD software that we saw in the video. And I'm going to go over this briefly. We'll talk about it a little bit more in part 3 when we go over thermal management. But just to review, here's our input power. You know, the biggest power consumer of this is going to be the motor drive. So I have a big trace and I have the motor drive chip as well as our big bypass capacitor real close to the input power. We have our smaller capacitor here and we have our Zener diode here. And so that power is feeding into the chip. There's 2 pins. I try to make the trace wide. And then on the bottom layer in blue, and so the red coloring represents the top layer, the bottom layer is blue. So where you see blue, that's the bottom copper, and the red is the top copper. And I'm showing the ground plane here. So let me actually turn off the ground plane. So here we can see this without the ground plane. And here's our chip. And then underneath, so this is where the A coil power supply is. Then underneath, I go to the B coil power supply. And notice on my pad that connects to ground, which was labeled EP, I have vias that connect this ground pad to the ground plane on the bottom of the board. And I do this is a little trick I like to do, and I've talked about it in past videos. Your PCB design software might throw up errors, but I just ignore them. But I'm tying these vias from the top thermal ground connection to the bottom to better dissipate heat. So when I spread my solder paste, these vias get filled with solder and it helps transfer the heat from the top layer to the bottom so it can better dissipate. Here's the pins for connecting the motor. Here's the pins for looking at VREF. So if you notice right here, here's my voltage divider network where we get the voltage value that sets the max current. Okay, if we go over here, here's our LEDs here for clockwise and counterclockwise that the ESP32 drives. A lot of these resistors are for setting those different settings on the IC that I talked about. Some of them are pull-up ones, some of them are pull-down ones. And you can see the various connections running from the ESP32 to the motor drive chip. Up here, I have the programming header for the ESP32, as well as some pins to pick off the 3.3 volts, as well as the UART, as well as ground. Here is my 3.3 volt regulator where I have some thick traces to help dissipate heat. I'll talk about that more in part 3. But this is the VCC signal coming into here that generates 3.3 volts to power the ESP32 as well as some other things. Here's my power LED. Here's the Zener diode protecting the 3.3 volts. Okay, that's it for part 2. I will have the hardware design files, the BOM, the schematic, and the Gerber files for this board on Patreon if you want to join and access those files. And then when we get to part 3, where we're going to cover the Arduino code in more detail, we'll look at another demo and we'll talk about thermal management. If you have any questions from this video, please use the comment section. And if you have anything to add that you think I might have missed, please use the comment section. Thank you for watching, and I'll see you back here for part 3.